Started here. I think there's a few people still strolling in, but figured we would get started with our meetup. First of all, thank you, all of you, for joining us today. I'll do a little introduction of myself and Branch and talk about what the meetup's agenda is, and then we'll switch over to the meat of it, which is this excellent panel of 5 data scientists who have lots of great war stories about how they've accomplished great heights in front of challenges where textbooks and traditional methods may not have applied, but they figured it out anyway. And I think this is a good tips and tricks for everybody that's in this field with which to figure out how to solve problems. I'll start with, we're at Branch. I'm the VP of Engineering here at Branch. My name is Mark Weiler. Branch is a 5-year-old company. We're in the space of solving mobile fragmentation. It started off as a company doing deep linking, which essentially is fixing HTTP on mobile apps, where you click on a link, and you expect it to go inside of the app, and when you're on your phone, and it goes into Safari or Chrome instead. That's a broken link, in my opinion. It should go into the app that's on your phone. So when I'm in my email and I click on a Yelp link, it goes into the Yelp app. It doesn't have to re-authenticate. I'm in the right contextual page inside of the app. That's one of the core problems we solve. We're also in analytics, reporting, and attribution. So those same vendors of those mobile apps use us with which to look at usage patterns of their users, to look at their advertising campaigns, to use us as a third-party independent vendor to determine who gets credit when they do an advertisement, and then somebody does install or do some action like an install or a conversion, then we're the ones who determine who actually wins that. We're in about 50,000 SDKs today, including a large, many of the large ones that are name brands that you can see up on the sheet there. We're about 350 to 400 people total in the company, and 100 engineers. That includes core data science, development, QA, and we're growing. So if you're interested, at the end, you can give me as well as any of these panelists, lots of interesting problems to solve. To give you some example of scale, because that's another relevant element to data science, we absorb on a daily basis tens of billions of events. And those events are things like mobile users opening or installing or doing a conversion. So those are really interesting kind of mobile data set and a very, very large volume. We use this, one of the use cases that I can share with you that we do with data science, and Eric can describe this in more detail because he helped to build it, is because we're the person who gets to determine who actually won on an advertising use case where hundreds of people advertise to you to get you to install, say, the Uber app. When you do actually install the Uber app, the person who last advertised in front of you gets the credit. And one of the things we have to watch out for is fraud, because there's people out there that have device farms and they're like doing fake clicks, they're doing all kinds of funky stuff trying to get that money. And we have to be able to detect that with machine learning. It's impractical to do it with just rules, because as soon as you set a rule, they will find a way around that rule in about 10 seconds. So that's kind of one of the interesting use cases we have. Today, the meetup is about making an impact in data science where traditional methods fail, or traditional methods are not something that you can apply. And traditional methods are things you learned in school, things you learned in the textbook, things that you can like read on the internet. How do you solve problems for your business? And that's the impact part, is that it actually impacts positively the business. How do you solve that when your prior experience or things you've learned or things that you've talked to friends weren't able to apply, and you got to be able to work around that and find a solution. And so we have 5 experts here who have a lot of experience. They're going to go through their background and talk about some of those experiences today, but these are like the war stories and tips and tricks that'll help you learn the tool set with which how to solve those problems. Their solutions may or may not work for what you're doing, but it's more about the mindset of how you think about solving that problem and overcoming those obstacles. That's one of the key things we want to try to convey today in our panel. So without further ado, I will pass down to each of the people to introduce themselves. And Eric Glover here is going to help us moderate as well. He's one of our principal data scientists.
My name is Eric Glover. I'm a principal data scientist at Branch. I've been here for almost about 3.5 years. I've worked on a variety of different things. As Mark was saying, you know, it's just awesome to be at a company with real true big data and big data problem. My background actually is I have a PhD from the University of Michigan from a long time ago when the world of machine learning was very different than it is today. And then from there, I went to NEC Labs where I did various research. My PhD and my research was usually on like web search and text search and large scale text classification in different languages. And then after there, I went to various different search engines, big and small, and now I'm here. And my background, like I said, is machine learned ranking, web scale search, categorization, and just general machine learning and AI. So, and then I'll pass it down. We'll all make introductions, and then we'll all share some interesting stories.
Thank you, Eric, and thank you, Mark, for having me today. My name is Halim. I am the Chief AI Officer of Cognoa. My background is in machine learning, search result ranking, like Eric. I did my grad school in machine learning at Columbia, and I worked there on machine translation and natural language processing long before deep learning, back when it was hybrid methods. I also worked on search engine result ranking at big and small search engines. I worked at eBay doing search result ranking for e-commerce in an environment where the results themselves changing dynamically with the auction market dynamic. I also worked in professional services doing big data science and engineering for multiple clients across verticals. I currently head the data science team at Cognoa. Cognoa is a healthcare startup in Palo Alto. We do pediatric diagnostics and therapeutics for behavioral health problems in young kids looking for signs of autism or ADHD using AI. And I'm going to share with you today some of the lessons that we learned there and other places I've worked before.
Hi, I'm Kevin Stumpf. I'm right now the co-founder of Tecton. It's currently still in stealth startup that is solving the data problems that are preventing data scientists from getting machine learning models into production at scale. Been working on that with a large team now for the last year and a half. And before that, I was an engineering manager and tech lead at Uber, working on their machine learning platform called Michelangelo, which is an end-to-end ML platform that allowed Uber to scale ML across the enterprise. And before that, I had a company which was an Uber for trucking, which is how I ended up at Uber. And that company was using machine learning to predict prices for truckloads, recommend truckloads to truck drivers, find good routes, and the likes.
Thank you. I'm Pardis, Noorzad. I'm currently head of data science at Carbon Health. Carbon Health is a tech-enabled healthcare provider designed to make primary and urgent care accessible to everyone by optimizing the delivery and improving health outcomes, which are both problems that my team focuses on. I also want to apologize for my voice today. This is a very recent development. This winter in general is something. But yeah, I checked the symptoms, it was different. Before Carbon Health, I was a data science manager at Twitter. Worked on a lot of the recommendations platforms on trend search events, Explore tab. Before Twitter, I was at Paytm. Worked on fraud detection for the payment system. And before Paytm, I was at RubyCloud working on promotions allocation for online and offline retailers. My background is in applied mathematics, where I worked on random graph models of online social networks. And also AI, I worked on music genre recognition. and sparse classifiers. And I did an undergrad in software.
Hi, everyone. Thank you for coming. My name is McPherson. My background is statistical signal processing, so I come at it from the signal angle. I think that's one of the things I love about machine learning and deep learning is you have the signal component to it, the computer science, the algorithmic component to it, and then the mathematical kind of theoretical component to it. So I come from this signal background, and after grad school, I spent a few years, 7 or 8 years, in closed rooms with no windows, working for a defense contractor on cybersecurity problems. And that led me from the signal processing background to the machine learning and deep learning. And about a little over 2 years ago, I joined Intel, and I'm part of Intel's AI lab, which is within the artificial intelligence product group there. And we focus on both applied and general research, as well as kind of optimizing models for Intel hardware. Within Intel, I manage the federal research team. So we do applied research with federal government and other government type organizations like the Red Cross. In my spare time, I volunteer at a local nonprofit called Delta Analytics, which is a completely volunteer-based nonprofit that works with other social impact organizations throughout the world to supply data expertise for these nonprofits that maybe don't have the skills. And we work on 6-month-long projects with these nonprofits to kind of give them the expertise and build solutions for them that they can go and take and utilize after we leave. And so, right, for Delta, I'm the director of project operations currently.
Pass it back to this. So now what I'd like to do is I'd like to ask all of us panelists to come up with a really cool story or 2 stories about something just really neat that you did that's, you know, outside the scope of things you can just Google for, right? So, you know, you have a problem. Many of us just go find a notebook, copy it, but sometimes that doesn't work. And so I have an interesting story from actually 15 years ago when I was at a company called SearchMe, where my job was to build the core categorization engine to classify for about 4 billion web pages into as many as 1,000 categories. And the thing is the challenge was not to say, we've already got this predefined taxonomy, but there was a person whose job was a taxonomist who in the future would decide arbitrarily which category seemed interesting, and then we'd have to just make it work. And we didn't have pre-labeled data. We didn't have, you know, a massive team of people to do it. And so the approach I decided to take was to use active learning. And an interesting thing about active learning is that normally, for those who aren't familiar with active learning, that the idea of active learning is that when it's really expensive to collect labeled data, rather than collect a large amount of just randomly labeled data, the computer will tell you which points make the most sense to label. So with a very small number of labeled data points, you can actually build pretty good models. And so when you have to come up with 1,000 categories, you're not going to get, you know, 10,000 points for each, right? So active learning makes a lot of sense. The problem with active learning, though, is the theory says you should pick the point on the margin, because that is the point of the highest model uncertainty, the point where getting a label will give you the most information. Unfortunately, that's also the point where when there's judge uncertainty, where the correct answer actually is, you know, 50%, that will also correspond to that same point. And if you actually ask someone to label a point forcibly with high uncertainty, that will completely screw up your model. And so the challenge is, how do you build a system where you have some taxonomist who comes up with some vague definition of some category, sends it to some labelers, and then use active learning where if they make a mistake or have an uncertain point label, it will screw the whole thing up. And so we came up with a couple interesting approaches to this. The first thing is that judges may actually know they're not sure about something. So instead of forcing the judge to give a label, we gave them the option to actually skip a point and to say, hey, you know, I don't actually know, let's exclude this point. And by excluding the uncertain points, that means that the label points have a lot more confidence and are more likely consistent with the definition of the taxonomist. In addition, the skip points can go back to the taxonomist to figure out how to clarify the definition. Another problem with, building classified models is actually the negative set. That when you're trying to train a classifier, it's not just finding good positive examples, it's finding a sufficient representative set of negative examples. And when you have a class with a high prior, say like sports, for example, then you may end up with positive examples in that class. And actually sports is an interesting one because that's an example of an uncertainty, to get back to the previous point, where like the taxonomist may say we have a category of sports. And then some judge is given an Amazon page for basketball, right? Is that sports or not? So you ask 10 people, 5 would say yes, 5 would say no. And if you forcibly label it, the classifier will get confused and it will do the wrong thing. And so likewise, you pick sports, you pick 1,000 random examples, or maybe some sports examples. And when you have very small positive sets, then that can actually also screw up the classifier. And so we created something called negative set cleaning. And so negative set cleaning allows the model itself, when you're training it, to identify points that are less confident. And then you can feed those back to the judge to identify if they're actually positive or negative or should be excluded. And so what was the third thing? And then the third thing is that we were doing feature selection for text classification. And when you have very small sets and you do active learning, you're picking points all over the place, you want to get clusters of points together. And so rather than picking points only at the margin, I also picked highly confident positive points to grow the positive set to improve the ability for feature selection. And so in the end, we had a very small team of like 5 or 6 judges and 1 taxonomist. And in a matter of like weeks and like months, we actually had 1,000 classifiers that had really high precision on like 4 billion web pages. And so, and so the point is that like understanding the limitations of the approach and then coming up with creative solutions allowed us to actually build a system that worked at scale. So I'm gonna pass it off.
Choco, right?
Yeah, exactly.
I remember that.
Yep.
So I worked with Eric at Search Meetup. I remember that story, kind of dating ourselves there. So the theme I want to share with you today is the power of incomplete solutions. Generally speaking, if you have unlimited resources, maybe every problem is solvable in traditional ways. But when you are working with limited resources, so you have limited time, limited number of people available, or limited data, and sometimes some problems become unfeasible. You just can't solve them with the amount of resources you have. And that just means that if you insist on solving them in traditional ways, you'll run out of money or run out of time, just not be able to solve them at all. So then you have to start thinking outside the box and say, well, I can't do a complete solution. I have to come up with an incomplete solution. Most incomplete solutions are useless, but the power of finding that incomplete solution that is useful, though incomplete, is a skill set that you kind of gain with experience. And so that's a very powerful trick. And I'm going to share with you a couple of short stories on that theme. So one comes from the time where I used to work for eBay, and we were working on a fashion design kind of shopping experience where you're in the fashion vertical shopping and you click on something you want to buy and it starts showing you similar items by color. So if you're like already in the jeans section and you click on one jeans and it shows you all kinds of other jeans within that same color theme. And it's kind of, it gives a better shopping experience. That's more than 10 years ago. So that's before the breakthroughs in computer vision with convolutional neural networks and all that. We were using more traditional methods. And we kind of had to whip that together in a week. I had 2 people. We had a lot of data. It's just we didn't have a lot of time to put it together. So if we were to put it together at all, we had to come up with a trick. The problem is a lot of times shoppers or sellers at eBay will put items for sale on top of very busy backgrounds. It would be like the kitchen or like a very colorful tablecloth. So if we were doing color similarity, it threw it off because of the background and it didn't work. We had to do a lot of sophisticated foreground versus background logic, which was not easy to do. And so the solution I proposed is, let's not do it for everything. Let's just do it for the subset of items that are photographed over white backgrounds. It's very easy to tell if the white background is white. You just look at the bounding box, you know, the outer ring, and there's a spike in the white color. That's a white background. And if you limit the method to the white background photos, color similarity works great. And that's a solution in a day or two that works on, say, a third of all items. It's incomplete, but it allows for a great shopping experience because a third of eBay items is a lot, and people will shop and they will not notice that anything is missing. And then we go tell sellers, well, if you want to be included in that first edition of the feature, make sure you take your pictures on white background. So you define the problem, and there you go. You have a workable solution right there by not allowing yourself to live within the scale of the problem as defined. Another example is from my current work at Cognoa. We build classifiers for diagnostics of autism. Autism is a rare disease. One in 50 children, or 1 in 60, depending whom you ask, will have autism. Currently, the problem, the unmet need here in America, is that the diagnosis of autism can only happen in specialty centers. Pediatricians can't diagnose it, so children will have to wait in line for like 18 months at a time. To some families will have to drive 200-300 miles to a specialty hospital to get their diagnoses, and that 18-month wait is kind of a missing of a critical window of neuroplasticity where therapy will have the best effect for long-lasting effects of the condition. So Cognoa is built using AI to build diagnostics that work limited only using the phone in the pocket of every parent. Whereas there's a lot of research on how to diagnose autism using fMRI machines or DNA sequencing. Well, the problem is parent doesn't have time to drive 200 miles to a specialty hospital, so the solution has to be more accessible, not less accessible. So we're trying to do it using smartphones. And there, the problem is using smartphones, what you can do is you can ask parents questions about the child. You can have parents film the child for a little bit and have people look at the film or do computer vision or computer audio analysis on the footage. During the early work that I started at Cognoa about 4 years ago, I tried using those modalities to build a classifier for autism that is diagnostic grade, meaning positive predictive value more than 90% and negative predictive value also more than 90% for it to be admitted as a diagnostic medical device. As hard as I tried, I just couldn't do it. Because in a lot of cases, autism is easy to detect using machine learning. In some cases, it's borderline. There's a big gray area where there's definitional noise. Specialists would disagree on what constitutes autism versus a condition confusable with autism. The 2 or 3 minutes of video that we're having the parent film and the few questions that we have the parent answer are not enough to call every case reliably. As much as we tried, we failed. And so basically, do we close shop and go home, or do we come up with an incomplete solution? So the incomplete solution we came up with in this case is to train a special classifier to detect those hard to call cases and flag them as hard to call cases. And then to train a second classifier to deal only with the easier cases and call them as positive for autism and negative for autism, resulting in a 3-pronged classification, positive, negative, or I don't know. And the I don't know fits very well in the doctor's clinical workflow because they are very accustomed to inconclusive test results. If a test comes inconclusive, they run another test, or they monitor the child, or they have them drive 300 miles to go to a specialty center. But for the 70% of the cases where it is conclusive, we are doing a big favor to the parent and the doctor, kind of streamlining the system. So this goes into as another example of a way to change how you look at the problem to come up with an effective solution that is not complete. Pass to you, Kevin.
Thank you. My theme is about how to scale the work of individual data scientists and of large data science organizations. And in 2015, Uber had figured out how to scale the organization. They figured out how to hire thousands of people, go into hundreds of markets, grow millions of concurrent trips, riders, drivers. They figured out how to scale software engineering and get software into production every minute, push updates out really any minute, any hour from any team. What they hadn't figured out was how to scale data science across the organization, with now hundreds of data scientists in the organization. And the state of the art in the organization of data science at Uber in 2015 was that different pockets of data scientists were using separate tools. There were no processes in place. It was easy for them to get access to a little bit of data, train a model, show that they could drive some business impact with it. But there was no real good way to get this model into production. It would take months, maybe longer than that, to get something out there. And so the Michelangelo team was tasked with building a platform that brings the best software engineering practices to data science and enable data scientists to get all the way from collecting the raw data on the one end through transforming the raw data into features to training the model, evaluating the model, and deploying the model and serving it at really, really high Uber scale and very, very low latency. And that was the problem that we solved there over many, many years. And we observed that by building this centralized platform, we were able to lead to this Cambrian explosion of machine learning within the organization, where later on in 2018, we now have thousands of models in production across tens of different teams. The company is literally using millions of predictions per second, all through that one platform, Michelangelo. And an interesting trade-off that we came across was that you always have this trade-off between flexibility and ease of use. And so first we focused on the standardized platform with a limited number of algorithms that you can train with the platform, which comes with its limitations, but also with the ability of the platform to actually save the user time. Because typically the more flexible a system is, the less time you save the user, the fewer guarantees you can make, the more things are going to break. And so we started off with this very limited flexibility, but it was still broad enough to solve hundreds of different use cases in the organization. But then later on, there were more and more demands to give people tools to bring custom models to the system. And then on this trade-off of very limited flexibility, but high scale, very easy to use, versus high flexibility and not very easy to use, we then added on to PyML. We blogged about this, and it's a very different approach where data science were then able to bring completely custom models to the platform, just wrap it up in Python, and then use the exact same infrastructure that we had built for the other side of the platform to deploy the model, monitor it, and serve it at really high scale. And that was a pretty fun journey. And we, in 2018, then looked at it very closely and tried to figure out what were the key components of this platform that allowed Uber to scale ML in the organization. And we realized that the greatest catalyst for the data scientists within Michelangelo was what we there called the feature store, which gave data scientists the ability to define a feature once using common terminology, define your transformations, give it a name, give it a bunch of other metadata. And then that platform made the featured data consistently available to data scientists when they interactively try out new models, made the data available to training pipelines that would, in an automated and repeated fashion, train models over and over again, and then made the same feature values also available to real-time models that were running in production at really, really high scale and low latency. And we looked at that and then decided to start a company around it.
Thank you. I have two stories. One is from Paytm, and Paytm at the time was actually somewhat earlier in stage to Uber. So when I joined the Toronto team, we had kind of 25 people. There was one team, okay, so we were tasked with fraud detection in the payments part of the Paytm app. Now, the app was run by 3 different kind of sub-organizations, one marketplace, payments, and mobile recharge. And because it was run by 3 different organizations, the data was separate. And so what we did on our team was to bring all the data together. And so our first project was to build a fraud detection engine. One group was a team of ML engineers, and we had some label data, and they were kind of exploring and finding ways to model the fraudulent activities that we had found to that date. There was a BI team, very strong BI team in Noida. They would identify all the different ways that fraud could happen, which was, because at the time we didn't have that much labeled data. So we needed to identify how can these 3 different apps be used in conjunction to, I guess, do money laundering or other things. So they would identify those and tell us. Then our immediate solution was we had a couple of people in the Toronto office building, using Hive rules to kind of stop the types of fraud that we were able to detect. Now, a lot of software engineers, data scientists aren't really well trained to write a modular SQL code. And so the Hive code very quickly became just unmanageable, very hard to read. And so our solution was, okay, let's move everything to Scala and Spark. And that was when I kind of realized that a lot of the features that we're building share a lot of commonalities. And of course, they're like very different when you explain them, but in implementation, they're actually sharing a lot of similar patterns. And so going back to the idea of like building a feature creation pipeline, which is kind of made easier with Scala and Spark because of the ability to compose functions. It's very easy to think about every new feature as like a composition of multiple of those functions and kind of build any type of feature you can think of. So we spent some time designing and building that. And we also, another added benefit of this like feature pipeline was that we could replay historical data through it to kind of identify how many people would get affected every time we would, like, let's say, put a rule into production. And we would also understand how much money would be in flight, how much would be in wallets if we were to block that sort of transaction or block the user. So suddenly we had like a whole lot of big statistics about any of that sort of action as well. So yeah, instead of going back and forth with the BI team, we're able to do a lot of those decisions on our side after they had, of course, identified what type of activity could actually happen. And suddenly we went from like 3 features a day that could be sometimes buggy to like 1,000 features a day, where we also kind of were in charge of estimating the thresholds, and we were able to monitor everything. Kibana add alerts, know exactly how many people were blocking, how much dollars are being blocked, and kind of have full visibility into that system. In addition, this system also provided a lot of good, clean data for the ML team, and good labeled data for the ML team to kind of build their models on, identify clusters of like different types of very different fraud families, and kind of build separate models for each. So it really helped on the modeling side as well. My second story is shorter. It's from Twitter. When I first joined, I joined as a data scientist on a relatively new infrastructure teams, and it was great because seeing like a company invest in infra is always very positive. They brought two very strong engineering managers, strong engineers from across the company to kind of back these two infra kind of investments. As I was working with the team very kind of a couple of quarters in, I realized the team is kind of doing a lot of the work that consumer teams, so teams that would be consumers of the infra would be doing. And I kind of, looking back, I was like, you know what, it's incentives, all about incentives. Metrics are very powerful. And when we don't explicitly define or set OKRs for a team, they will look to company OKRs, and in the experiments, they will try to like move company OKRs. However, with infra, a lot of times you actually don't, when you run an experiment, you don't want to move any metrics. It's actually better if you don't. That means you correctly replace one part with another without touching like the existing behavior. One, we set up additional metrics to run correct infra experiments, but then we also kind of joined the reporting structure for the infra team along with all of its consumers to ensure that the infra team is focusing on infra and the two teams are not really cannibalizing their impact. So that was the second story.
Yeah, so the theme that I'd like to kind of discuss was probably the main thing I learned in grad school. So this is like your 4-minute PhD here. Basically, it's a little bit different than the topic of when methods fail, but more when methods don't exist. Because a lot of times in research, you're working in areas that people haven't really touched. So there might not be existing methods, and it's kind of up to you to come up with those methods. And for me in grad school, it was, this is where I got started in cybersecurity and computer network traffic, and being in a signal processing major, trying to apply methods, machine learning methods, statistical methods to computer network traffic. There really isn't a sampling theory for computer network traffic. I mean, there's no Nyquist, there's no audio sampling rates or anything like that. So my first problem was, how do I represent this signal? And being a grad student, you read every book and you sit around and contemplate life for 3 or 4 months. And then you kind of come across a book that actually helps. And for me, that was, it was some theory in economics and industrial processes. And essentially, you gave me the idea of how to represent these computer network signals. And once I had represented them in this new way, the problems and the solutions became almost immediate. So I guess kind of my theme is, a lot of times when you're in a scenario where there aren't existing methods, try to reformulate the problem. Take a step back, look at it. Can you represent it in something you already know how to do? And kind of like the modern day equivalent of it is something that came up more recently, again, with cybersecurity. Being a deep learning researcher, we wanted to apply deep learning now, kind of upgrading what I did in grad school. We wanted to apply deep learning to computer network traffic. And again, it doesn't fit kind of the standard paradigm of computer vision or natural language processing or, kind of the standard deep learning models and technologies out there right now. If you're familiar with the computer, the cybersecurity space, a few years ago, some researchers actually did come up with a really interesting idea of reformulating packets on a computer network as images. It was a pretty brilliant idea, and they created images out of packets and then trained classifiers, and were able to detect a lot of malware in packets as they're transmitted on the network. Our approach was something different. We didn't want to to look at classification. We wanted to do something a little bit deeper. And we wanted to generate embeddings. You know, everyone loves word embeddings because they're really cool and you can do fun math operations on them. So we wanted to do the same kind of thing, but with computer network traffic. And again, there's no immediate way of doing that. But it turns out if you kind of represent the bytes in a packet as characters in a word or a sentence, you can apply the same natural language processing techniques to computer network traffic and develop really strong embeddings. So, you know, those are just two simple examples where there's just a slight reformation of the problem or reformulation of the problem, you know, can get you into a space where these methods do exist. And, you know, a lot of times they work really well in that space.
So now what I'd like to do is each of us would like to just come up with some kind of like recommendation that we can take home that will help us if we get stuck with certain kinds of problems. And something that I didn't really talk much on my story, but I think is really important is the problem of evaluation, right? If you're building some kind of machine learning model, you need some kind of evaluation methodology metric. And there's a lot of common metrics, F1, AUC, precision, recall, whatever. And I think a common mistake that people make is that they forget about the fact that there's actually a consumer of what you're building. And that's usually some kind of business application. So if you're at a company, you want to accomplish some business goal. And very often there might be like a disconnect between the metric that you're using and the true business application. So I can give you two like just kind of extreme crazy examples, right? Imagine you're building a classifier that's trying to look at a protein to predict if it could be like a cancer cure, right? You could have a really, really high AUC, but it's useless. But if you had even 1% precision, right, you'd be a billionaire, right? So, you know, you come up with 100 solutions, 99 of them are wrong, one is right, that's amazing. And so, like, you have to think about what it means in the context of the application, right? Another kind of extreme example is, you know, you're building a classifier to predict if the president is going to push the nuclear launch button. And it's going to run, you know, every second, right? Even if you had like 99.99% precision, the world is going to die, right? And so, again, these are kind of extreme cases. But, I mean, basically, the point is that think about the metric and then how it maps to what you're trying to do. And so sort of common mistakes that people will make is they'll assume all errors are equal. And as for my two examples, that's not always true, right? So you want to think about the metrics in the context of what do the mistakes mean, right? Another example related to metrics is this problem I call of sort of false optimization. And so I've seen a case at a company I'm not going to mention where they were trying to make a search product and they were trying to maximize the clicks, which seemed like a very natural metric and formally defined. You train your model, you see what clicks it would, you know, maximize. Great, everyone's happy. Except the problem is when you maximize the clicks, you don't actually maximize relevance. You maximize, you know, clickbait, right? You maximize things that aren't actually relevant, but fool people into thinking they're relevant, so they click on it. And so, again, this is an example where, like, the metric taken out of context of the application can create problems. Another very important thing related to metrics and applications is a common mistake that a lot of people make is that they evaluate things in one context and apply them in a different prior. So very often your labeled data may come from some set that may have a bias, for example. You know, like you look at people complain about facial recognition problems, right? That they screw up on large classes. And so it's very important to be aware of, again, what the metric means on your data. So some very specific recommendations are, before you actually apply something in a production application, actually look at a sample of the results that fall into different subclasses. Think about what those errors actually mean, right? Do they matter? Are they equal? Is it you know, testing high but going to fail in some horrible way, right? So actually dig in deep, take the time to look at it, right? look for like subclasses that might matter. And in some cases, when you discover a subclass of errors that actually matter more, you can sometimes come up with very cool solutions. Like a really dumb one that people might not think about is if you're building a search engine, sometimes taking the most popular examples and just hand labeling them can actually solve the horrible problems. And that even though your overall score may be really high, getting the 5 most popular queries wrong, people will never ever come back. So again, just think about the evaluation metric in the context of business application. So that's the advice.
Okay, so a couple of things. Don't be afraid to mess up your data. So it's a common mistake that solutions are as successful as data is clean and unbiased. In reality, your data needs to be as noisy and biased as the real life inference kind of environment where it's going to be, when your model is going to be run. Otherwise, the model is not going to work correctly. And so an example of that in Cognoa, where I currently work, we're training our predictors on historical patient records. So supervised learning with labels of here is a patient that had autism 7 years ago, and here is the kind of the profile, the phenotype of their medical record. So that's a clean data set. No noise in there, no missing data, no biases. Yet, what we're building is something that the parent is going to be using. We're going to be asking the parent those kinds of questions. The parent is biased, the parent is subjective, the parent is not knowledgeable. It's going to give us noisy data, biased data. So one way to solve that problem is to go to collect data from parents paired with diagnoses, but the problem is that takes years. It took years to collect those historical patient records to begin with. So what we ended up doing is we observed the kinds of noises and the biases we get from the parents, and we built a statistical model of how noisy and what kind of errors we get from parents. We injected that deliberately back into the clean medical data set in order to build a training set that's noisy on purpose. And that worked very well. It worked way better than training on the clean data. Another thing is keep in mind who is going to be using your end product, what matters to them. So one thing we're building right now, again at Cognoa, is using computer vision models and computer audio analysis models to take footage of children and try to assess whether they're high risk for some condition or another. Using deep learning, you can do amazing things these days. You can probably, build a monolithic network that can just take a full video as input and give you a confidence of, high risk for a condition as output. I wouldn't bother building that because no doctor will use it and no parent will be convinced with its outcome. The doctor will not use a medical device that's just black boxy and says, this kid has this condition. They will not trust it. They need to know why. They need to know whether they meet the DSM criteria for this behavioral problem or another. So it has to be something that maps to the semantic concepts that clinicians right now think of as the cause of some condition or another. Knowing that redefines the methodology of how you solve a problem. Even if solving it the monolithic way is easier, it's just not going to work. Kevin.
From my end, the advice would be to, when you embark on a data science problem, before you actually throw yourself into it, make sure that it's both organizationally and technically feasible to get this thing all the way out into production. Organizationally, this means that there is an executive sponsor for your project. If there is not, then nobody will stand up to actually make sure that the project will see all the way through to production. It needs to ideally be an OKR that your project, your data science project, is attached to. Otherwise, again, there will be no organizational pull and nobody will kick down the doors that are necessary to be kicked down to get the thing into production. Then equally important is that it's actually technically feasible to get this thing into production that you've built. Is it going to be possible to create and run the feature pipelines that then later on make the data available for your model? Is it cost efficient enough to run these pipelines and make the data available so that it is actually justifying the business value that your model is bringing home. And overall, I think it's important to look for opportunities to drive standardization while not stifling innovation. Because if you find these opportunities to drive standardization, you can learn from each other in the team. You can leverage each other's work. You can get help from other people. And standardization is the most important thing to get steps of a workflow automated. Without standardization, there's no repeatability, and without repeatability, there's no way to automate things. And you need automation to be truly empowered to get your work into production. And there are many different ways and many different pockets where you can be looking for standardization and best practices that you can use to really increase the leverage that you have as a data scientist to get your work into production quickly. Software engineering has a lot of best practices that you can learn from. For instance, the data science code, the modeling code, the feature engineering code should all be Git-backed, version controlled. It should be fully reproducible. You should look at tools like DBT to break up these giant SQL DAGs that we just heard about into individual modularized components that are easy to understand, easy to test, easy to automate, easy to version control. Look at CI/CD pipelines from the software engineering world to automatically train models, integrate them, test them, and then push them into production. Look for ways to organize the data and the models so that other people can easily find the data, find features that you created, share them with others. There are really cool new open source tools that you can use for that stuff, like Lyft's Amundsen is actually a really cool tool to organize the metadata of your data, make it searchable, make it discoverable, find the stuff that is actually valuable for other people that's worked for them so that you can reuse it. And then finally, also don't be afraid to go a level deeper as a data scientist and go deeper into the world of a data engineer, become more familiar with their techniques, with their platforms. Learn Spark, learn PySpark, learn DBT, and many of the other good software engineering practices that have really driven this DevOps flow for software engineers that nowadays allow software engineers to go from a code chain to production literally within minutes. And the same thing is possible for data science as well.
Yeah. I think Kevin really drove home the point of what I want to say. And it's really, let's not reinvent the wheel for both data science management and data science best practices. In data science management, we can learn from design teams, we can learn from engineering teams. Long-term ownership is important, focus is important, and similarly on the engineering best practices side, let's just transfer them over. All of those things are there for a reason. And so I recently tweeted SQL is code and and it received so much good support because people really feel this. So yeah, I guess Kevin said this better. Let's just transfer all of those good learnings into data science and build tools for them.
I think the thing I like most about data scientists is we're currently in this current generation. There's such interesting, diverse backgrounds of people coming into it. People coming from physics, coming from the social sciences, coming from economics, from math. I think I don't have a lot of the business practices to teach you. I do research, so I don't mess with business or anything like that. But what I will say is, for yourself, really, use your background to the best of your ability, but then really develop in diverse number of areas. I think the common concept is be T-shaped, be really deep in one area, but really, have a lot of breadth in a lot of different areas. And I think in data science and machine learning, that is such an important thing to really strive for. Again, it kind of goes back to my point before. Being able to reformulate problems. You can only reformulate problems if you have an understanding of all these different areas. If you don't understand economics, you can't make a transition to some economic model for your data science. So really just kind of, always be learning, always be looking into new things, reading things, even if you don't think it's going to apply. You'll be surprised at how often it happens to me all the time where, I'm reading an article about economic policy and just an idea, you can think about it, think about your problem in some way that kind of fits to that economic policy or to something else. So, learn visualization, learn all the different areas of data science. Like Kevin said, learn data engineering, learn software engineering, have a little bit of depth in all those different areas because it'll just really help you be able to kind of rethink when you get stuck. You'll have so much other areas to kind of reach out, and you'll have so many different ideas that you can utilize in those areas.
So yeah, so thanks everyone to the panelists. What I'd like to do is open up to questions, a couple questions. We have another microphone somewhere. I don't know what. Right here. Here we go. So if people have questions for any of us, a couple questions. Raise your hand. Oh, let me make sure my mic's on. Is it working?
Testing?
Yeah.
Yes. Thanks for this wonderful panel. I was wondering if anyone felt that data scientists deserved a more nuanced taxonomy of what data science is for them. And yeah, how would you break that down? Thanks.
Look like you wanted to comment? Anyone?
I completely agree that you.
Sean?
Yeah, I mean, I completely agree with you. I'm not going to take on the task of defining this taxonomy. But yeah, again, I think, as I just mentioned, the data science that is such a broad field, and you have people, it really depends on the company. I think you have these data scientists at smaller companies, where they do everything, from data engineering all the way through visualization. So it really kind of depends on the company. But once you get into the larger organizations and the larger data science teams, they're definitely a specialization. I know, to me, not to be biased or anything, but the machine learning role, it's kind of people either want to be a machine learning engineer or a data scientist. There's a lot of people that have issues being called a data scientist if they think they're, a pure hardcore machine learning engineer. So I think there needs to be some definition there, as well as, in a few different areas. But again, I'm not going to take on that role.
Anybody else want to comment on that? Sure. You had a question, Tim?
I'm formulating it, so
okay.
I'll find out. Here we go.
All right.
Please remind me your name.
Halim.
Halim and Kevin. Halim, you had said keep data dirty. Kevin, you had said you're trying to clean data.
Yeah.
Fight.
So I think both is actually correct. And
Let's ready to rumble.
I can take him on.
so it's definitely 100% important that if your production model sees dirty data, then your training processes need to see dirty data too. However, you still need to be able to manage that dirty data in a clean way, in a central place.
Yes, and so to be more specific than what I said before, don't be afraid to dirty your data to the extent that it needs to be dirty in order to work well in real life. You want to make sure that it is at the same level of noise to signal ratio that you'd expect to see at inference time. No more, of course.
Good.
It was fun to
Yes.
just
Sure.
point that out.
Maybe one more question.
Yeah, just maybe for Halim and so like when it comes to dealing with or
creating models for healthcare systems, how important is causality compared to correlation? Because like machine learning is all mostly correlation in a way. And when you're dealing with, say, like doctors and they want like certain proof of certain thing causing something, how do you get around that? Is this something you face?
Right, yeah, so that's a good question. Generally, when we're doing our R&D, we're not really focused on the difference between causality and correlation. We're working traditional machine learning methods, trying to build predictive models that work on, that generalize well on held out sets and all that. When you hit regulatory bodies like the FDA for diagnostic devices or therapeutic products, the way they will enforce that causality assurance is by constructing properly blinded clinical validation tests. So if our therapeutic is supposedly causing benefit or an improvement in a certain aspect, and the way we would prove it, it would have to have multi-armed test sets where different subjects are subjected to different treatments. We have to come up with a sham. So we have to come up, if we're building an app that's helping children with social responsiveness, we have to build another app that doesn't have that, method of action and is otherwise similar to our app to show that it is not a correlation, it is a causation. So there are systems in place to make sure that nothing gets out there without having that checkbox checked. But it's kind of further down the road and a little bit removed from the R&D process.
Our current models don't necessarily try to find that or solve those types of problems. Our current model that we have is like a clinical decision support system that actually take all the tests and the results of the tests. So they're not really generating new types of knowledge, but are just, really learning existing knowledge. And in the future, as we kind of, have more primary care patients over time and can follow, what they're doing and the impact on their health, we might be able to do studies like that where we are also contributing to the kind of medical literature.
So, all right, unless someone has any burning questions, thank you guys all so very much for coming. Hopefully you guys got some kind of goodie bags. There's another bag in the front for people, I guess, take one.
People who sat in the front row get a bag.
Yeah, thank you guys very, very much. We recorded this. We're gonna post it up online soon. So yeah, so thanks everyone.
Thanks everyone. Some great insights today. I'm sure if you want to stick around a little bit, I'm sure people will have some questions as well for the next 20, 30 minutes. There's also some food in the back if you guys are still hungry. Once again, thank you for coming in. Appreciate it.
Thank you.
It's great. Yeah.